Hello, my name is Mrs Kershaw and I'm one of the Science Directors with Outward Grange Academies Trust. Today we are going to look at states of matter. During today's lesson, our challenge is going to be to describe the arrangement of particles in solids, liquids and gases, and then our aspire is to be able to explain the change of state in terms of particles, energy and forces. Right, to get started, I'd like you to grab a pen and a piece of paper and write down everything that you know about the three states of matter. That's solids, liquids and gases. Include diagrams of the particles and think back to things that you might have done in both chemistry and physics. 2 minutes, off you go. Okay then, let's grab a red pen, and as I go through each of these, then if you've missed something out, then add it to your notes. So first of all, looking at solids. Solids cannot be compressed. That is because all the particles are tightly close packed together and touching in all directions. This means that solids will keep their shape, and generally solids tend to be strong. Do you think the forces between the particles in a solid are weak or strong? Well, the forces in a solid are very strong. Okay, moving on to liquids then. Liquids, surprisingly, cannot also not be compressed, and that is because the particles are still touching. They're more irregularly arranged, but they are touching, so therefore we can't manage to squash them any closer together. But because there is a little bit of movement in the particles, liquids can flow. So thinking about the forces again then, do you think the forces between particles in a liquid are weaker or stronger than a solid? Yes, that's right. They're generally weaker than the forces that are in a solid. Finally then, if we look at gases, gases can be compressed, and that's because their particles are all spread out and there are gaps between the particles, so you can force the particles closer together, enabling them to be compressed. But just like liquids, gases can move, and that means that they can flow. Do you think the forces between the particles in a gas are weaker or stronger than a liquid? Yes, that's right. They are weaker than a liquid. So far we have described the arrangement of particles in solids, liquids and gases. I'd now like you to evaluate the simple particle model. I would like you to make 2 columns, and one column will be the good things about the model and the other column would be the bad things about the model. Because this is the evaluate command word, we want to be looking at the pros and cons of each. And don't forget, if you can, to justify your conclusion. Okay, so here's a table. Good things on the left side, the pros, bad things on the right side, the cons. 2 minutes, pros and cons of the particle model. Off you go. Right, so let's have a look at some of the things that are the pros and the cons of the particle model. So first of all, one of the pros is it provides us with a simple visual model, something that we can easily see and use to explain our theories. So the second one, it can be used to explain the properties of solids, liquids and gases. They're the things like, can they be compressed, can they flow, and later we can look at how this can explain melting and boiling points. Disadvantages then, this shows that all particles are spheres, and that's not necessarily the case. Secondly, there are no forces between the spheres. We can't see anything. The particle model seems to infer that the spheres, that the particles are all solids, and that all the particles are the same size, have the same mass and the same energy. And if we think back to our models for elements and compounds, all the particles appear to be elements. So you see there's rather a lot of disadvantages to the model, but at the same time the fact that it is simple and gives us a visual model that helps us to explain things means that it's really useful to use. So I just want to remind you at this point about state symbols. They tell us a lot about what is happening in a chemical reaction, and if we look at this equation below, you can see that a small s in brackets would tell us that in this equation the sodium is a solid, water is a liquid, and here the sodium hydroxide that is produced is an aqueous solution. That means it's dissolved in water. And finally, H2 has got a G after it, so that means hydrogen gas is produced in this equation. These are really, really useful things, and in an exam these will always be given. Okay, so just a bit of a recap then. Matter is the term that's used to describe any material. There are 3 states of matter, that's solids, liquids and gases, and most materials can be changed between these states. Can you remember what we need to do to change state, and what are the changes of state called? So what did we call it when we go from a solid to a liquid to a gas to a liquid, and a liquid to a solid? 2 minutes, write down as much as you can remember. Right, so how did you get on then? When we go from a solid to a liquid, this is called melting. And then when we go from a liquid to a gas, that is boiling. Going the other way, a gas to a liquid is condensing, and a liquid to a solid is freezing. And for each of these, we will also need energy. So as we're changing a solid to a liquid and melting it, we will need to provide the particles with energy to do so. When we know the boiling and melting point of something, then we can work out its state. So using water, we know that water melts at 0 degrees centigrade and it boils at 100 degrees centigrade. So what state is water at minus 12 degrees, and how can you tell this? 30 seconds. If we look at where minus 12 would fall on the number line, it is to the left of 0. This falls into the solid region, so at minus 12, water would be a solid. Using the same principle then, methane boils at minus 160 degrees and it melts at minus 180. What can you tell about the state of methane at 12 degrees centigrade? 30 seconds. Well, in this case, 12 degrees centigrade would appear on a number line far to the right hand side and well into the gas region. So therefore, at 12 degrees centigrade, methane would be a gas. Okay then, your turn to have a go at these. I'd like you to copy the table and decide for each of the substances whether they would be a solid, a liquid or a gas at room temperature, and I want you to assume that room temperature is 21 degrees. 2 minutes. How did you get on then? So, bromine at 21 degrees would be a liquid because you can see that it's higher than its melting point, but 21 degrees is lower than its boiling point. Chlorine, on the other hand, and fluorine would both be gases because both of their boiling points are less than 21 degrees. Finally, iodine would be a solid because its melting point is 114, which is much higher than 21 degrees. So at 21 degrees, it would still be a solid. Okay then, so the amount of energy needed to change. The bonds inside the molecule are very strong. It's the size of the attraction between the molecules that matters for melting and boiling point. So looking at these hydrogen chloride molecules, the bonds in the molecule, the intramolecular force, is very, very strong. But when we change this to a liquid and a gas, we do not break the bond in the molecule, we just break the intermolecular force between the molecules. Okay, so we've managed to explain the change of state in terms of particles, energy and forces. Okay, now we're going to have a look at a 6-mark question. The question tells you that bromine boils at 59 degrees centigrade. Chlorine boils at minus 34 degrees centigrade. What state are these elements at room temperature? Can you describe what boiling is in terms of forces and then explain why these two elements have different boiling points? This is a longer mark question, so we're going to use bug. So if we box our command word, this question has 2 command words. The first one is describe. Describe what boiling is in terms of forces. So we need to say what something is like in this example. Our second command word is explain. So we're going to have to give a reason why these two elements have different boiling points, and we're going to need to use the word because in there as a connective. So you are explaining that something happens because of. We underline the keywords, they have different boiling points. So we need to be referring to the boiling points, the point at which it changes from a liquid to a gas. And then if we glance back over the question, we need to make sure that during our answer we reference that bromine boils at 59 degrees centigrade, whereas chlorine boils at minus 34. So what I want you to do at first is I would like you to spend just 2 minutes planning this. That's not writing it, just planning the kind of things that you're going to include in your answer. Off you go. Okay, so we've planned our response now. What I would like you to do now is I would like you to spend 5 minutes writing your answer. Off you go. let's get a red pen then and see where we managed to score some points. So first of all, you needed to say that boiling is a change of state from a liquid to a gas. You needed to say at room temperature that bromine would be a liquid, it hadn't boiled, and chlorine is a gas and it had boiled. And the explanation for this is because bromine has stronger forces between the molecules. We could call those intermolecular forces. And that means that it needs more energy to separate the molecules into a gas. If we then compare this to chlorine, chlorine has weaker forces between the molecules, so therefore it needed less energy to separate the molecules in a gas. If you need to pause the video and amend your answer, then do so now. Okay, well done. That is the end of today's lesson. The following slides have a summary of all the key points that we've covered today. So if you want to record that in your book, then pause the video and make some notes.